Let us understand the concept of sampling distribution. Sampling distribution is the probability distribution of a sample statistic. A sample statistic could be your mean, your proportion, or your variance. So let's look at the formal definition of sampling distribution. It refers to the probability distribution of any sample statistic. Let us understand how the sampling statistic is generated. We draw out a sample from the population and compute the sample statistic and record it. We draw another sample with replacement and compute the sample statistic, record it, and we repeat this process for a large number of times. Theoretically, we repeat this process infinitely, but practically, say 10,000 would be a good reasonably sized number of samples that we can draw to generate the sampling distribution. So sampling distribution of the mean describes the probabilities attached to all values of the mean of samples that are repeatedly taken from the same population. Let's look at it pictorially. We have a population with any arbitrary distribution, and we draw out a sample which has its own respective probability distribution. We compute the sample statistic and record it. We repeat this process for a sufficiently large number of samples, and then we take these sample statistics and develop the sampling distribution. The sampling distribution has very interesting properties that we are going to use to build our central limit theorem. Another important term to understand here is the standard error. The standard deviation of the sample statistic is called as standard error. Let's try out a small little experiment to understand how the sampling distribution can be generated and what is the true nature of the sampling distribution. So let us say we want to compute the sample mean of a sample, and let me generate a very arbitrary distribution. So let's say rand between two numbers, and let me also randomize that also. Rand between, let's say we generate 1 to 10 as the lower end, and we generate rand between let's say 90 and 100. So we are going to generate a set of random numbers which will be between 1 to 10 and 90 to 100. So that would be kind of bring in sufficient reasonable randomness. Of course, all the numbers will be between 1 and 100, but I am not limiting it to only two specific values. The end points every time would be different. And let's kind of generate a large number of sample. How large? Let's kind of use the entire width. I think 814. Let's kind of make it a sample of size 1000. 940. Okay, so we are at 1022. So we have generated a sample of size 1000, as we can see here, and let's generate a large number of samples, let's say 10,000 samples. All right, so okay, so here we are. So we have generated 10,000 samples of size 1000. And let us compute the sample mean, average, is equal to average, command shift right arrow key. So we get the sample mean, and let's compute it over the 10,000 samples. And then let's draw the histogram for this. Now this is the distribution of the sample mean. So this reasonably looks like a normal distribution. This is an empirically observed phenomena for any sample statistic when we draw out a large number of samples. Hope you understand the concept of sampling distribution. Now we are going to formally establish the relationship between the population distribution and the sampling distribution, and that relationship is called as central limit theorem.